There are many examples in physics, biology, and chemistry where you'd want to mix types of motion. And you have a mix of fast-moving and slow-moving objects. For example, say we have some group of relatively slow-moving or crawling biological cells, and they interact with a relatively fast-moving fluid, say blood flow in a say blood flow or some other liquid flow, and we would want to treat the dynamics of our biological cells and the fluid separately. So that's basically what we call a multi-scale problems. And particle dynamics lets you model a wide range of these kinds of phenomena. So uh, what we wanted to do in Mechanica is make it really easy for people to choose the appropriate equations of motion for the problems that they're trying to solve. So this example here creates a single large particle that, and in this case, this happens to be an immobile particle, but we could easily create two particle types where one obeys Newtonian dynamics and the other one obeys overdamped dynamics. And we can change the dynamics simply by setting the dynamics equals overdamped. The particle dynamics, it defaults to Newtonian dynamics. And I got a quick little demo here where I create a large particle, a small particle, and I'm going to run two different simulations here. One with a small particle being overdamped, and the other one with it being Newtonian. And then I simply bind a soft sphere interaction potential to both between the small particle types and between the small and large particle types. And then I create an initial condition where I basically create a sheet of, here. I basically create a sheet of small particles that are sitting above the single large particle. So, and I do all of this with, probably about 15, 20 some odd lines of really basic Python. So let's go ahead and run this and show what kind of fundamentally different behaviors we get. So we can simply run these two scripts here. So the left is Newtonian dynamics, and the right here is overdamped. So let me zoom these in a bit. And we can see that in the overdamped case, because there is no inertia, the particles just simply suck in to the large sphere that they're attracted to, and then they form basically a sheet, and the surface tension, or the attraction between the small and large particle will tend to drag this sheet of small particles over it. And if I let this run for a while, we will see this one actually completely envelop this larger sphere here. And we look how qualitatively different behavior we get when we use the Newtonian dynamics propagator. Because we have the exact same potentials, exact same forces in both of these models here, we can see that these small particles are statistically attracted to this larger one, so there's a much higher density of particles around this regime, but they're not actually binding to it because they are inertial in this case. And we can see that both of these simulations are actually running concurrently, and they're both running in real time. So I think I have each one is using 4 compute threads and 1 GPU thread for each one. So, Newtonian dynamics, and overdamped dynamics. Thanks for watching.